Alright, what we're trying to do is we're trying to find the equation of an osculating circle. We've already found the equation of an osculating plane in the previous video. We used r of t is 3 cosine t, 3 sine t, t. We defined a function for the unit tangent vector, and then one for the unit, the principal unit normal vector, which is going to be important in what we're about to do. I found the unit tangent and the unit normal vectors. I cross product those because that's going to give me a vector normal to the plane that contains those two vectors, and those two vectors are in the osculating plane. So this was normal to that plane. I found a point in the plane, like so, and then I found the equation of the plane. What I wanted to do to clean it up was I cleared that because it's equal to 0, so it doesn't really matter, to give me this. And then what I actually did after that was I solved that for z so that I could use this a little later on, because I'm going to have to replace the x and the y with some parametric equations. It's going to be a little messy. So far I've been using Grapher to graph this and see how it's going. So you can see we have a corkscrew curve. We have the point that we're looking for. And then we have the osculating plane, which seems to be doing a good job so far. So the unit tangent vector and the unit normal, the principal unit normal vector are in this plane, or parallel to this plane. And the unit binormal vector is normal to this plane. So that's what we have so far. And now what we're going to do is figure out the equation of the osculating circle. So to do that, I'm going to need the radius of it. And the radius is actually the reciprocal of the curvature. So what I need is curvature. So the curvature is a function of t is what I'm going to define here. And it is the norm, which is menu 77, but I'm going to type it, of the cross product, which you can get from menu 7c, and then select it, but again, faster to type it, of, so it's the first derivative. I'm going to use a dummy variable here. The first derivative, so r prime, crossed with the second derivative, or r double prime, of, ooh, that would cause me a problem. It's supposed to be a z. R double prime of z. And then I'm going to divide that by the norm of, and it's back to r prime. And then I have to cube that. And then what I want to do is at the very end, I'm going to switch my z back to t. So I get that, and now I can find the curvature as a function of t. In this case, something weird is going to happen. I get 3 over 10 because for a corkscrew curve, the curvature is always constant. It's always, well, what in this case, 3/10. For other curves, it could be different. So if you change r of t, it's going to change the values there. It'll give me the same thing, but I'll do it anyway. Our curvature of pi over 6. And that gives me 3/10 again. So the radius is the reciprocal of that. So the radius is 1 over the curvature at pi over 6. So that's the radius. Now, what I want to do is I'm going to start at the point that I know, which is r of pi over 6. So that's the point that I know that's on the osculating circle. And the center is always in the direction of the unit normal vector. So I'm going to move in the direction of the unit normal vector, and how far do I want to move? I want to move the radius, like that. So that gives me the center of the osculating circle. So now what I'm going to do is I'm actually going to write the equation. So to do that, I'm going to go back to Grapher. So it's negative radical 3 over 6. So let me go, I want a new equation, and from template, and I'm going to do a Cartesian curve, like so. So x is negative, nope, that's y, negative, and then it's square root of 3 over 6. So that's a center, and then the radius is 1 over the curvature, or 10/3. I'm going to go with cosine of t. For the y coordinate of the center, it was negative 1/6. So let's go back, and I'll go with negative 1 over 6. That's a 5, negative 1 over 6, plus the radius, which is 10/3, and then sine of t. And now what I want to do is I need to make sure that these are at the right height. So I'm going to take the equation of the plane that I got, copy this, and I'm going to replace the x and the y that are in it with the parametric equations I just wrote for x and y. So I'm going to replace x with, copy that, change this to parentheses and paste that, and replace y with this. And this will give me the correct height. So I already knew the equation. So I'm basically finding the intersection now kind of a right circular cylinder with this plane. And the intersection will be the osculating circle that I'm looking for. So there is the osculating circle. And you can see that it's doing a really good job of approximating the curve at that point. And that's how you do it. So the key thing here was we knew a point. So r of pi over 6, or if you have a different value, it would be r of whatever that value is. You want to move in the direction of the unit normal vector. So I did plus the unit normal vector. And then how far do you want to move? You want to move the radius. And the radius is the reciprocal of the curvature. And that's how you do it. So this pi over 6 is just the z coordinate you get at the center. So I didn't actually need that to write the equation of the circle. I just needed the x and y so that I could write the parametrics for the circle, and then take those, plug it into the equation I got for z. I actually used my calculator at some point to solve for z here to clean that up. So that's how you do the problem. I hope you found this helpful, and good luck.